Good evening. My name is Darren Law. I'm in Section 1 of Fundamentals of Physics. I'll be doing my podcast on the effects of pressure in a liquid. The way I'm going to start off this podcast is actually giving you guys a good demonstration of what I'm talking about. So far I've got a clear 16-ounce disposable cup. I went and took the liberty of taking a permanent marker and just drawing some rings around it to show divisions within the cup itself. Next, I'm going to grab my knife here. Alright, and I'm just going to punch 3 pin-sized holes inside this thing, so give me a minute. Alright, I'm going to just punch 1 hole in each individual level itself. Alright, that's 1. 2. And a little bit bigger than that. Great. Alright, 3 holes inside each individual layer within the cup. I know it's kind of far away, there's no way you guys can possibly see it with that camera, but hey, pretend you can. So, next thing I'm going to do is I'm going to grab my thing of water here, and I'm going to top off this cup. Let's observe what happens. Alright. Now, we got water coming out the top layer here, we got water coming out the second layer here, and we got water coming out the third layer here. But there's something very unique actually going on here. All the water is not exiting at the same speed. Why? I mean, it's a cup with holes in it. You would think, why? It would, right? But no, it doesn't. That's what we're going to discover today. Why it doesn't exit at the same speed. So what I'm going to do is take this little water and just pour it back in my little container here. So give me a minute. No, you got to preserve what you can, right? Alright, cool. Let's sit there and chill for a minute. And I guess I'll start explaining, trying to explain why this happened the way it did. Well, the force that's active upon it, 2 forces actually, that are active upon it. The first one being pressure. The second one being gravity. But the main one that plays the biggest part is pressure itself. So let's talk about it. To talk about it, we must first define what pressure really is. Pressure in the terms of physics is defined as a force per unit area. It's usually more convenient to use pressure rather than force to describe its influence upon fluid behavior. This is represented by a simple formula. It's pressure equals force over area. Simple enough. That's why you geeks out there, I'm going to break this down a little bit simple for those of us who really don't know like formulas. Let's say we in a water environment. All right. Now, when you swim underwater, you can feel water pressure as you know on your eardrums while you're swimming, right? Well, the deeper you swim, the greater that pressure becomes. Well, what causes this pressure? It's simple. The weight of the fluids directly above you plus air pushing against you. That's all it really is. As you swim deeper, the more pressure is, the more water there is above you. The more water there is, the more pressure there is. Simple enough, right? So if you swim twice as deep, twice the amount of pressure. Kind of coincides with each other, right? Added to the water pressure is pretty much the pressure of the atmosphere itself. Atmospheric pressure doesn't stay constant, but it's enough to actually give you a level. Pretty much 10 meters of water depth, and you actually get a significant change in pressure. Those who actually scuba dive would actually notice, because you must equalize yourself as you go deeper into water. Every 10 meters or so, you must equalize yourself. If not, it's painful. It's quite excruciating if you don't do that. Because of the atmospheric pressure on the surface of the Earth is nearly constant, the pressure difference you only feel under the water is only caused by the changes of depth itself. So, the pressure due to a liquid is precisely equal to the product of the weight density times the depth itself. We give you that pressure. That pressure does not always depend on the volume of the liquid. So if I were to take this container right here, poke 3 holes in it, and the exact same thing will happen. Even though it is about, well, I don't know, 50% more than what this cup is, the same effect will still occur. even though it's a larger mass. The volume or how much water you have does not matter. The only thing that plays a factor itself is how deep or how much depth is in that water itself. That's the only factor that really plays into it. Now, liquid pressure is exerted equally in all directions. For example, if we were to submerge ourselves in water again, it makes no difference which way we tilt our heads at certain depths. The pressure will not change because the pressure itself is omnidirectional. Take for instance, you have you go to the beach again, and you have a ball. We all know that everything has an opposing force to it. The ground, table, whatever you use. Water does too, because like I say, it pushes in all directions. If you try to take a beach ball and push it into the water, you will actually feel resistance as the ball tries to go in, because the water is actually pushing it back against it. Same thing with a boat. A boat is exerting a certain amount of force on top of the water, where the water is actually forcing, using the amount of force equal to it, pushing back up. So that pretty much shows that pressure in water does not always go down in this one direction. It actually goes in all directions. All right, and we know that pressure acts sideways. As we can see, water spewing out sideways and leaks in upright cup. So that's even more proof that water does not always have pressure going downwards. Ours get leaked out the side. So when water presses against the surface, a net force is directed perpendicular to the surface. If there is a hole in the surface, the liquid will spew out of right angles of the surface before curving down due to the effects of gravity. The greater the depth, the greater the pressure, therefore increasing the exit speed on which the liquid will exit. So, in layman's terms, because this hole is at the bottom of this cup, due to atmospheric pressure actually pushing down on the liquid itself, plus the weight of the water itself, the water at the bottom of the cup had more pressure on it, therefore allowing it to exit the cup at greater speeds than the middle, and much more so than the top. So, just to see it again, let me put some more water back in this cup. Alright, cup's topped off. Water's coming out of here, here, and here. But the reason it comes out so much faster from the bottom is because pressure from the atmosphere itself, plus the weight of the water, allows the water at the bottom to exit at much greater speeds than the middle and the top itself. So, in a nutshell, that is the differences of pressure in a liquid. So I hope you enjoyed this podcast. Thank you and have a nice day.